Now let's start the second chapter numericals of NCERT, which are of the utility and certain specific questions and discussed. So we go about for the numericals. First question is there. It's 2.4 numerical. Conductor radius is given, charge is given, and you have to find electrical field inside the sphere, just outside the sphere, and a point 18 centimeter from the center of the sphere. Remember, the radius is 12 centimeter, and that 18 means you have to go outside the sphere. First part very clear, that within conductor the electrical field will be 0. Second part, because at the surface we will take k cube by r square, straight away formula we get 10 to the power 5 Newton per coulomb. For the third case, we will consider as the charge has been kept at center. So r will be 18 and we get the value. Remember, whenever you are outside the sphere, you have to calculate by k cube by r square, considering that r is there itself from the center to distance. Second question, 2.8 parallel plate capacitor. It has given the distance between the plates, area, that means you can know the capacitance also. Charge to 100 volts and find the charge. We first find the capacitance, epsilon naught A by D. You place odd D values. We get 18 picofarad. Now it's corrected to 100 volt. Q is equal to CV. We get 18 nanocoulomb, 1.8 nanocoulomb for this. Straight formula, nothing specific. Now, this is the question 2.12, in which you should remember you have to find the work done taking a charge. Electrostatics force is basically state function, just like gravitational force. So what are the differences? The main aspect of this type of forces, it will not depend on the path, it will depend only on the state. That means you have taken the charge from P to Q, your R point is irrelevant. And secondly, the change in energy is equal to work done. So we'll try to find the energy at point P, considering one charge at over there, other at origin. Similarly at Q, and we'll find the difference between them. The formula for the energy is k q over q2 by r. We place the first energy, u1. We get the second energy also, u2. Remember, in this case, since the coordinates are 0, 0, 3 and 0, 4, 0, we have to find the basic distance from the origin 0, 0, 0. So we have converted, and the difference now is should be the work done, which is 4.8 joule minus 3.8 joule. Here again, you remember that the point r was irrelevant. Next question, two spheres, distance between them given. Find the electrical potential at the midpoint and the field at the midpoint. You see, for the A part, potential being a scalar, we have to add it up. For both the cases, the point is lying in between. The distance will be 0.15 meter, that means 30 centimeter divided by 2, because that's the distance between the two charges. You want at the midpoint. That is the main thing. So you find the potential. Second part, it says you have to find the electrical field. Now remember, within two similar charge bodies, the electrical field opposes each other. So it will be Q1 minus Q2. We try to find the same value and we get it. In second case, what it states is the distance of 10 centimeter from midpoint. So distance of either point from the charge will become root 325. And how do you get 325 is? The distance between the charges is 30. You divide by 2, 15. So 15 square plus 10 square. On the next page, you will get the complete diagram in the electrical field question part of it. Here you can take it, root 325 is the distance. Now here you again get the formula. Here it's important. See, it is 2.5 microcoulomb over here, 1.5 here. So one field will go E1 like this, other field E2 will go like this. So this is E1, this is E2. It is written E2 here, E2 is here. Angle are alpha and beta. Remember, alpha equal to beta. Now this is 10 centimeter, this is 15. So how much does it become? 10 squared plus 15 squared to square root. That's going to be this distance. Now we have got two electrical field at that point. Since we have to find the resultant, we have to break into horizontal and vertical components. Now, E1 cos alpha will be here, sin alpha will be here, E1 cos beta here, sin beta here. Now you can say all vertical components get added up, horizontal gets subtracted. So we write EH is the horizontal, that is E1 cos alpha minus E2 cos beta. In this case, since alpha equal to beta, we convert into a cos alpha only. Similarly, EV, the vertical component gets added up, we get this. Now, we try to find E1 and E2. Remember over here, the distance will be again root 325. So we convert. Charges is given to you, k cube r square we use. But again, now we have to use the cos and sine. Let's see. From the diagram, we can say cos alpha is 15 upon root 325 and sine alpha is 10 upon root 325. Because alpha or beta are basically these angles. This is alpha, this is beta. So this is the triangle which is to be taken into consideration. We take that, place the values. So E vertical, net E vertical, the one what we wanted to calculate over here, multiply by sine alpha gets this. Similarly, what we get E horizontal, by this formula we get like this. Now net will be, you know, E horizontal square plus E vertical square taken square root, and this is what we get. But again, this is a vector quantity. So vector does not require only magnitude, it does not require direction also. So we have to find the direction, and direction tan theta will be again vertical component upon horizontal component. So tan theta is 6.1 divided by 2.3. So theta comes out to be roughly 69 degrees. But the angle is from the line joining 2.5 to 1.5 microcoulomb. This was slightly tricky question using the vectors also in. So you should remember this is how you have to resolve the vectors in electrostatics. Next question. The inner sphere, external sphere are there. The inner radius, outer radius, both are given to you. Charge is placed as center. You want surface density at the inner and outer surfaces. The first part. Second is obviously a conceptual question. Let's go for the first part first of all. You see the spheres, concentric sphere shell is produced. R1 is the inner and Q is charge given. R2 is external radius. Now, when I place Q inside, because of this positive charge assuming Q, minus Q will develop somewhere over here. Total charge developed will be here minus Q. So that's what we show, minus Q. So when minus Q develops, some extra plus Q will develop along with it. So along with it, the outer periphery of the larger sphere, you will add Q plus Q. That means this charge is now a new charge. This is no longer here. So we remove this charge. This is now the outer charge. This is inner charge. Now you want the surface charge density. You know this is the charge divided by 4 pi r1 square. And if this is the charge, this is the 4 pi r2 square. And that's what we try to find it out. Outside charge, Q plus Q. There's an error over here. It's not minus Q. It has to be plus Q here because minus Q is inside. Plus Q again comes here. This is the thing. Slight error in the writing or typing. Please take care of that. Now, as per Gauss law, what he says that you want to find out whether it is not exactly a spherical unit, but any other conductor, any other cavity. So remember one thing, for the electrostatics, the electrical field inside conductor has to be 0. Because if there is field, it will start moving. The charge is available, that will start moving, and when it starts moving, it will become current electricity. So remember, by Gauss law also, there is no charge or net flux important. Similarly for the electrostatics. Next question. Now, this is a typical question. Some people might find slightly different. You see, you have got to find number of capacitors. You have got large number of 1 microfarad capacitor which can withstand 400 volts, and you want to apply across 1000 volt. We know the voltage gets divided into series. That's why we have to add number of capacitors in series. So remember, if I add 2 capacitors, the voltage across since the original voltage of supply is 1000 volt, the voltage across capacitor will come out to be 500 volt. Again, the capacitor will burst out. So we require one more share. So we take, let us apply 3 capacitors in series. So every capacitor will have 333 volt. Now it is safe enough. That is how we try to find how many capacitors are to be added in series. We can take it mathematically also. 1000 divided by 4 comes out to be 2.4. So we have to add slightly next higher digit. So next higher digit is 3. So we take 3 capacitors in series. But when we take 3 capacitors in series, the net capacity will be 1 by 3. But I want 2 microfarad. So I want many parallel connections of this. Lot of parallel loops for this. So when I take n number of parallel connection, so n into 1 by 3 microfarad should be equal to 2 microfarad, which gives n equal to 6. So that means you require in a row, you require 3 capacitors and you require 6 such rows. That means the total number of capacitors required will be 6 into 3, that is 18. So remember this type of question we have to do. This is a typical question. This you might require in current electricity also, the basic concept. Now, this is just like our series parallel question, the video you must have seen. We want the charge across and voltage across each capacitor. Now you should see over here, the important part is these two are in series. So net resultant is 1 by 200 plus 1 by 200 chi inverse, that is 200 micro picofarad. I'm not writing picofarad, it's all in picofarads. Now, this combination of these two and this are in parallel, but this is not in parallel because of this drama. You can see the word, had this line been straight, these two would have been parallel. But since this is not there, this is parallel this only. In other way, you can mentally take this negative terminal over here and make a straight line. So what you will get, some capacitor over here. So these two were in series, this in parallel, this whole combination in series with this combination, that is C4. That's what I have done. So C1 to 3 is 200. So C1 to 3 and 4 are in series, the net is 200 by 3. Net important thing is, now we have the net equivalent capacitance we have got. We should find the net charge. Net charge is 20,000. Now this charge will appear in all the series combination, which is this and combination of this. That means you can say at least that C4 has got this much charge. So we'll try to find what is the voltage across C4. That is 20,000 divided by 100, we get 200 volts. Now among, this is 300 volts, this is 200. So the voltage left across these two capacitors will be now 100 volts only. So we have to take that only, that voltage across C1 to 3 is 100 volts. And C1 to 3 means C1 and C2 3 in parallel, and in parallel voltage is constant. And hence C1 and C2 3 both will have voltage of 100 volts. Now voltage is known to you, we can again find charge. Charge on 100 is 10,000 and charge of combination of C2 3 is 10,000. So C2 C3 charge 10,000, we find the voltage also. Voltage across C2 C3 is 50 volt. I have given you charges and voltage, but remember the charges on this should be equal to this. C2 C3 must have same charge, and the charge combination of C1 plus C2 combined is in series with C4. So C4 should have same charge as these two. So this is 10,000, this is 10,000, makes 20,000, and C4 is 20,000. So it is coming out to be same. For better such type of numerical, you can go for my series parallel combination video. Now next, there is the 4 microfarad capacitor, 200 volt supply. Now it is disconnected from the battery and connected to another uncharged capacitor, 2 microfarad. How much energy, blah blah, we have to find it. First thing is the initial charge will be Q is equal to CV, which will not change now because you should remember battery has been disconnected. Basic fundamental of such numericals you should remember that when battery removed, charge will not change, and when battery connected, voltage will remain constant. So in this case, since battery has been removed, we try to first charge, initial charge, Q is equal to CV, which is 8,000. Now the charge will remain same because now battery has been disconnected. But the capacitor would change because now 4 and 2 are kept in parallel. Remember, 2 capacitors without battery will always be connected in parallel. They cannot be connected in series. So new capacitor will be 6 microfarad. Now the voltage will be, Q will remain same, capacitance changes, so it's 400 by 3. Now we should find the initial and final energy. So see, I am using the formula Q square by 2C because Q is constant. You can use half CV square, but for that V is changing. The concept is whatever is constant, we should try to slightly reduce our calculation base. So initial energy is Q square upon 2C, 8 millijoules. And final will be Q square upon 2C. Q will remain same, but C instead of 4 will become 6. So it's 16 by 3. So we subtract, and that's what we get the loss in energy in this type of capacitor. In such capacitor, we are assuming that both the things, capacitors, are added with positive added to positive, negative added to negative. Secondly, you should always remember that energy will be lost in such combination, whatever you do, because where does the energy go? It goes in heat, light, sound. So you should remember the voltage has to reduce, the energy has to reduce. So this is all about numerical. Now we go to next numerical. This is slightly theoretical also. You want the force on the one charge plate. We can calculate by two methods. First method is electrical field due to infinitely large sheet is sigma by 2 epsilon naught. So we place another plate there. So we get Q into E. So E is sigma by epsilon naught into 1 by 2. So we multiply, we get the answer. But that is the another method, because you can say the other field is also there. So we go for the energy conservation part of view. We are saying the capacitor has the area A, distance between the plates is D. So we energy at any voltage we are trying to find Q square by 2 epsilon naught A by D. Okay, Q square by 2C. Now we are taking the condition that the charge is not changing. That means once the capacitor has been charged, battery has been disconnected. Now I try to increase the distance between the plates by some amount, let's say D plus X. So this is the new energy now. I have taken D plus X here. But when you try to find the difference, you will get this. That is the difference between the energies. Now this energy difference should be equal to work done. That there lies the basic concept F into dx. So we try to find F and we try to simplify it. This is Q square upon epsilon naught A. So this is Q by A epsilon naught is E. That's how we go for this type of question. Here the half factor has come because there the field is in the two plates. One due to other, two due to one. Because of any one will be half. That's the basic of this. But you have found the calculations over here also. Third video will come soon about the current electricity. Thank you. All the best. For more such videos, please remain connected to my YouTube channel. Thank you.